moving on. A little bit more about Kw, and then we're going to practice some problems with it. So remember Kw, we call this the ion product constant for water, and it's a constant, okay? It's a value that does not change. So you ready? Here's the value. Kw, and I warned you, it's really small. It's 1 times 10 to the minus 14. That is the smallest value for K we've ever seen, because even if we go back up to this table where we had all these different K values for weak acids, none of them are times 10 to the minus 14. The one that comes closest is times 10 to the minus, well, I wrote over it, is times 10 to the minus 13. That's the smallest one we have, but Kw is even smaller than that. Kw is times 10 to the minus 14. Now, what this means, because Kw is a constant, in pure water, that means the concentration of the hydronium ion is equal to the concentration of the OH minus ion, okay? Essentially what we're saying is 1 times 10 to the minus 14 equals the concentration of H3O plus, I'm just plugging in the value here for Kw, okay, into this equation, times the concentration of our hydroxide ion. Now let me ask you this. If we're looking at this equation for water down here, every time one water acts as an acid molecule and one acts as a base, you will inevitably get one hydronium ion and one hydroxide. You cannot get one without making the other. Okay, so that's why the concentrations of these things in pure water have to be equal. And if they're equal, what that means is we take the square root of 1 times 10 to the minus 14, and you should get 1 times 10 to the minus 7. That is the concentration for these ions in pure water. Remember, I'm going to circle this 100 times. This is only for pure water, all right? But this is the concentration of these things for pure water. Okay, now let me ask you this. You know, things can never stay simple. We have to complicate them. So let's do that now. Well, consider this question right here. I'm still in eraser mode. How does the equilibrium of the dissociation of water shift if we add hydronium ion to the reaction? How will the equilibrium of this reaction down here, how will it shift if we add hydronium ion? You thought you were done with Le Chatelier's principle, didn't you? This is totally a Le Chatelier's principle problem. Equilibrium shifting, that's Le Chatelier's principle. So what we're saying is if we increase the concentration of this right here, how would equilibrium shift? According to Le Chatelier's principle, when you increase the concentration of a product, equilibrium will shift towards the reactants. So the answer is equilibrium will shift left. And it will use up some OH minus, okay? If we add H3O plus, it's going to use up some OH minus to react with the extra hydronium ion that was added. So that's this statement down here. Because of this shift, and because Kw is a constant, this number cannot change. If H3O plus, the concentration of it, or the concentration of OH minus increases, the other must decrease. Mathematically, that makes sense. To keep a constant number, if this goes up, this must go down. Okay? All of that to say, if we know the concentration of one, meaning H3O plus or concentration of OH minus, if we're given the concentration of one of those, we can always find the concentration of the other. Okay? Now we're going to practice this. Put it into practice. Practice problems with Kw. So I'm going to write our equation for Kw right here. Kw equals the concentration. If your head is swimming right now, don't worry. We're about to work this out and make it easy to understand, hopefully. That's the goal. So there's our concentration, or our equation for Kw, and we know Kw equals 1 times 10 to the minus 14. you also need to memorize this. Okay? So let's look at this question. It says, what are the concentrations of hydrogen ions and hydroxide ions? Remember way back when we started this chapter, we said hydrogen ions, H plus, is the same thing as H3O plus. They're the same thing. So whether we say hydrogen or hydronium ions, doesn't matter. Okay? Hydrogen ion, hydronium ion, same thing. So what are the concentrations of hydrogen or hydronium ions and the concentration of hydroxide ions in a 0.1 molar HCl solution? Okay, how the heck do we go about answering this? First of all, whenever you have a problem like this, you need to ask yourself, step number 1, what kind of acid or base is this? When you are dealing with acid-base problems, you need to identify, is this a weak acid or a strong acid? Is this a weak base or a strong base? Okay, HCl, let's go all the way back up to our table. Here's the table of strong acids and bases. You will have this table on your exam, so you can go look at it. If we're doing this problem, where is HCl? Here it is, right here. So notice it's a strong acid, HCl. Now, what does it mean if you're a strong acid? What it means if you're a strong acid, remember, is that you completely disassociate. So we're actually going to go write this equation right here down on our problem. Go back down to our slide. Okay, so we have HCl. We have identified this as a strong acid. And what do strong acids do? They completely disassociate. Okay? What that means is if we have it with water, we will get complete disassociation. We will have all H3O plus and Cl minus at the end of this. Or you could just write it like this. HCl disassociates into H plus and Cl minus. It's usually understood that water is present, but you don't have to write water in there. Okay, so both of these equations are sufficient. Now remember, the question here is, what are the concentrations of hydrogen ions and hydroxide ions? Well, if I have 0.1 molar of HCl to begin with, when I'm done, I'm going to have 0 of this. And every time one molecule of HCl breaks apart, I get 1 H plus and 1 Cl minus. So if all of it breaks apart, I'm going to end up with 0.1 molar of H plus and 0.1 molar of Cl minus. So bada bing, we already answered one part of this. What's the concentration of hydrogen ions? We just answered it. 0.1 molar. The reason this was so simple is because we're dealing with a strong acid here, and this is what strong acids do. The part we don't know is, what is the concentration of our hydroxide ions? Well, if we know Kw, our friend Kw, we know two parts of the equation. We know the value for Kw, 1 times 10 to the minus 14, and we now know the concentration of H plus. And remember, H plus and H3O plus are the same thing. So we now know the concentration of 2 of the 3 pieces of this equation. Here's what we know. Kw equals, I'm just going to write it. Okay, remember, H plus, this is H3O plus. Don't freak out. These are the same thing here. So we know Kw, 1 times 10 to the minus 14 equals, we know H plus, let's plug that in, 0.1 molar, and we're looking for the concentration of OH minus. So all we do is we divide both sides by 0.1 molar. Also, don't freak out that Kw is unitless, okay? I'm going to make a point of that. Unitless. No units. So we're going to divide 1 times 10 to the minus 14 by 0.1, and I believe that you should get 1 times 10 to the minus 13 molar is the concentration of OH minus. Okay? So now we've finished both parts of the problem. We figured out the concentration of H plus by determining that we're dealing with a strong acid and understanding that strong acids